Hello and welcome to physics. Today we're going to look at the gas laws. The first gas law that we're going to investigate is Boyle's law, volume and pressure relationship. This is the only law that's part of the IGCSE syllabus, but the other two is also quite interesting and good to know. So in this law we are comparing volume and pressure. So what we can see over here is a pressure gauge, and here at the bottom is the size of our container. So what we see is if the volume is small, the pressure is 23.4. As I increase the volume, the pressure decreases. So that tells me that the pressure is inversely proportional to the volume. Now what does that mean? In physics we use proportionalities, and basically when we've got a high pressure we've got a low volume, and if we've got a big volume we've got a low pressure, and the graph looks like this. Okay, and that gives us the value that pressure times volume is constant. Okay, so when we make that, we add a constant. If we make that an equal sign, we make that a constant. You'll learn this in extended mathematics. So therefore, pressure times volume gives me a constant value. And from that, if pressure 1 and volume 1 is constant, and pressure 2 times volume 2 is constant, we have this formula known as Boyle's law. Okay, so that is the first relationship. Let's look at an example. In this example, we'll be watching what happens if you blow a balloon under the water and you rise to the top. What happens to the volume? Remember, there's a lot of pressure underwater. As you go higher, the pressure decreases. So this is at 3.2 meters, and he's got a balloon there, tiny balloon. Now he's going to go higher up, showing us the head. Tighter and tighter, and if it can't expand anymore, it will burst. The next law that we'll be looking is Charles's law, which is the relationship between volume and temperature. So in this, we're now going to heat up. We've got 100 molecules inside the container. We're keeping the pressure constant, and what we're going to do is we're going to see that as we heat up, to keep the pressure constant, remember the pressure is the amount of force per area, so the amount of collisions between the particles. So to keep the amount of collisions the same, we need to increase the volume. When we make it colder, we will decrease the volume. And then the pressure should decrease. An example of this is what happens to a hot air balloon. Here they are blowing up hot air balloons. As you heat up the gas, the volume expands. We have air pressure here, normal air pressure. We're not in a closed container, so the air pressure can't build up. As the volume expands, at a certain stage, we will see that the balloons will start to take off. So as the temperature increases, the volume increases. That is Charles's law. So with Charles's law, we saw that the temperature is directly proportional to the volume. So if there's a high temperature, there's a high volume. If there's a small temperature, there's a small volume, if we keep the pressure the same. So the relationship between pressure and volume is directly proportional. And then if we want to make that an equal sign, we have to add a constant. So volume over temperature is constant. Okay, if you put the constant on that side, And that brings us to volume 1 over temperature 1 is volume 2 over temperature 2, and that is known as Charles's formula, Charles's law, but this formula is not part of the IGCSE syllabus. Next we'll be looking at a Montan's law, or formerly known as Gay-Lussac's law, which is the relationship between temperature and pressure. So in this law, we are going to keep the volume the same. So as I heat it up, the particles move faster, colliding against the sides more often, which increases the pressure. Okay. If I cool it down, the particles collide less, and therefore there are less pressure. So the higher the temperature, the higher the pressure, the lower the temperature, the lower the pressure. So in this video we will see what happens when you heat up a deodorant can or aerosol can.
A big hole takes up the car's sunroof, and inside, a charred mess. Mother Christine DeBrecht says when her husband first noticed the damage to their daughter's car, they couldn't figure out what happened.
We were all just shocked. We had no idea what happened. We thought maybe something fell from the sky or something like that.
And when they got a look inside, they were still without answers.
It looked like a tornado hit the inside of the car.
Until they realized this white residue was dry shampoo. 50 feet away, they found the bottle that was missing the bottom of the can.
If that had happened when she'd gotten in the car after work or gotten in the car to go somewhere, the glass itself would have been devastating.
Christine says the explosion was so powerful, her daughter's center console lid had been blown off the hinges. Her daughter just bought the car 3 months ago and used her own hard-earned money to pay a hefty down payment.
Terribly upset. She looked hard for a car that she wanted and could afford, and it's a real sporty little Honda Civic hatchback. It's a beautiful little car, and she's so thrilled about it, and she's just heartbroken.
This mother is just relieved her 19-year-old wasn't hurt, and she wants others to be aware of what can happen if products like this are left in a hot car.
I just want moms and kids to know that this product that they might be carrying around with them could be dangerous.
So in this law we saw that temperature is directly proportional to pressure. So if I have pressure and temperature, okay, let's just swap these two around, pressure and temperature, we'll also have a directly proportional line, which means we can make it equal by adding a constant, and if that's a constant, pressure 1 over temperature 1 is equal to pressure 2 over temperature 2, and this is the formula for this law. So as I've previously discussed, the only law that you need to know and to be able to apply is Boyle's law for volume and pressure. The other two was just extra to understand where and how the relationships are. I hope you have a nice day, and if you've got any questions, let me know.